It was the very first worksheet I gave you. So just once again, flip that over to the back. You'll see these columns right here. The other thing you will need out is a formula sheet that I gave you that has all of, hold on, I think I get this go down here, all of these formulas that you see in this box in here that I copied from the book. So it's all about the rotational inertia formulas of the hoop, the cylinders, the pendulums, and all that good stuff. So make sure you got that formula sheet out at the same time. Let's go back up here real quick. Feel free to stop this video at any time so you can keep track. Rotational inertia is just like regular inertia. If you remember, objects at rest want to stay at rest, objects in motion want to stay in motion. So the resistance of an object to change rotation is rotational inertia. Objects that are not rotating want to stay not rotating. Objects that are rotating, that should be a space between that a rotating object, wants to stay rotating around the same axis. So nothing wants to actually ever change its direction. The law of conservation of angular momentum is very much like the old one that we use. Remember, momentum cannot be created or destroyed. It's always constant unless an outside force acts on it. Well, now angular momentum is constant unless an outside torque or force acts on it. Now, what you have to do on number 3, it says, what is the moment of inertia? Moment of inertia is exactly the same thing as rotational inertia. So if you look at these formulas down here in the chart, okay, you're going to want to get that chart out. The first one says, what is the rotational motion of a hoop that is spinning like a wheel? So we're going to use this one right here. It says I equals mr. Now, don't use the one that says 1/2 mr squared like this one right here, because that one's spinning like a coin would on a table around an external axis. So we want a normal axis like a spinning wheel. So I'm going to use I equals mr. And in this case, it's the Greek letter iota. And so I'm going to put in iota equals mr squared. I'm going to put in my mass of 5.5, no, that's 5 kilograms. Thank you. Put my mass of 5 kilograms. And then we're going to put in our radius of 0.25 meters and square that schlatt mammy. And then you end up getting the answer of 0.3125. And you simply stick the units together, so it's kilograms dot meters squared. Now we're going to do the same thing, but I also have on my desk a solid wooden cylinder. And if you look down here at the formulas for the solid wooden cylinder, it's 1/2 mr squared. So it's going to come down here, look right down here, and you'll see the green that I'm circling here is 1/2 mr squared for the solid cylinder. And so the inertia of that will simply be 1/2 the answer I just wrote down. So 1/2 of 5 kilograms times 0.25 meters squared ends up equaling 0.15625, not dealing with any significant figures there. Once again, kilograms dot meters squared. On the next one, I ask, what's angular momentum? Well, inertia in motion is momentum. So now we have something that's actually moving in a circle is going to have angular momentum. And I'm not sure why the L, they use this. But anyway, we're going to use the italicized L to signify angular momentum. And the way we're going to get that is we're going to take the inertia times its speed, just like the old formula was mass times velocity. Remember that old formula we used where momentum equals mv? Well, mass is the same thing as inertia. So I'm going to use the rotational inertia. And instead of using v, remember we're now using omega. So I'm going to take my answers. This is for the hoop. So I'm going to take my answer from number 3, which was 0.3, I forgot what it was, 125 kilograms dot meter squared. Then I'm going to multiply that by the rotational velocity. Well, that sort of stinks because they gave me 4 revolutions per second for rotational velocity. Remember, you can't use revolutions, you got to use radians per second. So the way you change that is in 1 revolution, there are 2 pi radians. And so when you multiply that out, you end up getting 7.85, and the units are nasty here. You just shove them all together. And you get kilograms dot meters squared. I don't know if that radian canceled out or not. I'm going to put it in there, but I think it cancels. All over seconds. So pretty nasty units for that. Now it says, what's the angular momentum of the hoop in number 3 if it's rolling at a speed of 4 meters per second? Remember to convert meters per second to radians second. So let's go ahead and do that first. So I'm going to take velocity equals, once again, 4 equals omega times r. So again, we got to find omega here. So that would mean that omega, we'll divide both sides by r. The r's cancel out, so omega equals velocity divided by r. Let's figure out what this is then. I'm going to take the 4 meters per second, divide it by the radius. Oh, what happened to my... I don't know if I'm still recording or not, guys. Hang on. I think I am. There I am. Sorry about that, guys. I thought I stopped recording and I didn't. Hope I didn't say any potty words. Anyway, let's come on down here real quick. Okay, I'm going to divide it by my radius of 0.25 meters. And so that gives me 16. Now what we got to do is we got to throw in the formula here of iota omega. So L equals iota times omega. So I'm going to take my iota, which was 0.3125. And this was the momentum of the hoop again. And I'm going to multiply that now by the 16. And you end up getting the 5 kilogram meters squared radians over seconds. Sorry about that. Now, lastly but not least, we've got this ice skater that's spinning around. And in the conceptual physics books, it gives you a real easy formula. We're just going to use that one. Of when an ice skater has her arms out, she's going to have one angular momentum, and since momentum cannot be created or destroyed, it has to be equal to the momentum when she has her arms in. So I could say the L out has to equal the L when her arms are in. And the formula in the physics book that it gives you is mass times velocity times radius. And so I'm going to have mass times velocity times radius when her arms are in. This is her radius when her arms are out. And so the ice skater has a mass of 90 kilograms. Her velocity is 2.5 times per second. I'm not going to really convert that right now because they didn't give us enough information to do that. And then the radius is 1 meter here. Her mass doesn't change. I'm going to try to figure out what her velocity is when her arms are in. And her radius when her arms are in are 0.75. And so we divide both sides. The 90s end up canceling out. Because we're on both sides. We're going to divide both sides by 0.75. Divide this side by 0.75. And when she brings her arms in, her radius, not her radius, but her velocity actually increases from 2.5 up to 3.3 revolutions per second. And so what we're going to do now is we're now going to get ready to go out on the in the hallway and actually have you sit on a chair and try this. Hope you have a great day, everybody, and hope this helps get the notes down for you. Thanks for all your attention. Love ya. Bye.